So, just a reminder, worksheets 16 through 18 will be due on the 16th. That's in a little while. Homework number 2 will be due on the 16th. And exam number 2 will be on the 16th. That is the scheduled time in the previously listed schedule. The lecture is ahead of schedule, so we will finish chapter 18 well before then. Sign-in sheet is up here. I'm not making anything due any earlier. Oh, we need to turn this on. Things work better when you turn them on. So we were talking about precipitation. So if we want to go over how precipitation forms, there's two main processes. In a cloud, the tiny droplets that make up a cloud are less than 20 micrometers across in diameter, so they're less than 0.02 millimeters. So they're very tiny. And so they fall incredibly slowly. They basically will just stay along up in the cloud. So in order for them to fall, they need to get bigger somehow. And there's two main methods. There's the Bergeron process, where when the temperature in the cloud is below freezing and water droplets mix with ice crystals, it turns out ice crystals attract water vapor more strongly than water droplets do at these temperatures below freezing. And so the ice crystals will collect water vapor and grow bigger, while the water droplets will all shrink. And eventually the ice crystals will get big enough to fall as large snowflakes, and they can fall to the ground as snowflakes if it's cold all the way down, or they can melt on the way down and fall as rain. So if you have cloud droplets and you have an ice crystal, there's a temperature range where water vapor is more attracted to ice than it is to the cloud droplets. So it has little bits of water vapor move in and out of the cloud droplets. They're more attracted to the ice, so the ice will grow bigger, while the cloud droplets will shrink. The other method that can occur is what's called the collision coalescence process. This primarily happens in warm clouds and lower latitudes. It also happens in the lower portions of clouds where the Bergeron process is happening in the top. So large hygroscopic condensation nuclei form large droplets. Once you have a droplet that is big enough to start falling, it will collide with other droplets as it falls and get bigger and bigger. And basically sweep through and get bigger and bigger. So typical cloud droplets are really small. You get a large one. That large one starts to fall, collects material, gets bigger and bigger until about 5 millimeters, where it splits into several smaller ones that again sweep up material, and this builds up as rain. So the forms of precipitation that you can observe, well, in the way of just water falling on your head, you could have rain, where droplets have at least 0.5 millimeters in diameter. These are raindrops. They're of substantial size. Then you have drizzle, where the droplets are less than 0.5 millimeters in diameter. And lastly, you have mist, where the droplets are just big enough to be felt. Then you have snow. Snow is when you have ice falling, ice crystals or aggregates of ice crystals falling from the sky. This happens with the Bergeron process. You form ice crystals, it's cold all the way down to the surface, the ice crystals fall to the ground. There are several other types that can happen if you have a serious thing where you have some warm air above some cold air. So you could have the snow melt into rain and then refreeze. So sleet is cleared to translucent ice pellets. This occurs when warmer air overlies colder air. The rain freezes as it falls. So snow in the cloud, it melts at some height when it hits the warm air. then it freezes again when it hits the cold air at the ground. Glaze or freezing rain is when rain falls as supercooled rain. This is when that warm layer is thicker, or the cold layer at the bottom is thinner than with sleet. And you get an impact with a solid. So it's supercooled rain. So the raindrops are cooled below freezing, but they don't quite have a nucleation point. So as soon as they hit a solid, as soon as they hit something, they freeze and turn to ice. And so they cover everything with a glaze of ice. So if there's this thing where this is the cutoff where it's warm enough, snow falls down, the snow melts to form raindrops. Here the snow melts to form raindrops, then it hits a shallow freezing layer, and those raindrops get super cooled, and they'll freeze on contact. Here the snow melts to form raindrops, and it hits a deep freezing layer, and so there's enough time for it to become little ice pellets, and this is sleet. And then lastly, we just have snow, where no melting occurs. Hail forms as hard rounded pellets. In large thunderhead cumulonimbus clouds, you can get convection currents that go up and down repeatedly. And so basically you get a little bit of ice, and then each time it cycles up and down, it gets exposed to warm and cold temperatures, and it gets some water, and then it freezes, and it gets some water, and then it freezes, and it builds up in layers. So you get concentric shells. Most diameters range from about 1 to 5 millimeters. Most hailstones are little, but they can get quite big. They occur in large cumulonimbus clouds with violent up and down drafts, where layers of freezing rain get caught in up and down drafts in the cloud, and each time something cycles through, it builds a layer on and builds up, and pellets fall to the ground when they become too heavy. So basically you have some nucleus or embryo, it goes up and then down and then up and then down and then up and then down and then eventually falls. And you can get something large like this. Now mostly when you get hail, it's a lot smaller than that hail piece. I don't know, most of the times I got hit with hail, they're like this big. Still not pleasant. Rime forms on cold surfaces. It's the freezing of supercooled fog or cloud droplets. It's just, you have very cold fog or cloud droplets hits a surface, nucleates, and forms these spiky ice growths, like you can see here. As opposed to frost, which is the water vapor in the air condensing on a surface. Now, if you want to understand precipitation and what's going on with precipitation, you need to measure it. The easiest form of precipitation to measure, and the most common form of precipitation, is rain. The simplest way to do this, you put out a tube and you measure how much water fills up in the tube. Now, for actual meteorological instruments, they use something called a standard rain gauge. A standard rain gauge is a tube with a funnel on top. It's not that much more complicated. So if you buy a rain gauge, a cheap rain gauge at like a big, at a garden store or something, it's just a tube. And it fills up and you measure how hot. But if you're doing meteorology, you'd like to be able to measure as accurately as possible. So what you do is you use a funnel, and your funnel, the top of your funnel has an area 10 times that of your tube. So your tube, the height of the tube is 10 times what you would get in just a regular rain gauge. That's just a tube. So that makes it easy to measure small variations. So it uses a funnel to collect and conduct rain, and there's a cylindrical measuring tube that measures rainfall in centimeters or inches. And the idea is that for a standard rain gauge, the area you're collecting from is 10 times the area you're putting your water into. So your height is going to be 10 times as big, so it's easier to measure. Because if if you're measuring like a part of a centimeter, well, multiplying it by 10 makes your life easier. So here, a simple rain gauge is just a tube. 1 inch of rain leads to 1 inch of water in the tube. Simple and straightforward. A standard rain gauge has a collecting funnel and a measuring tube, which has 1/10 of the area of the funnel, which means 1 inch of rain leads to 10 inches of water in the tube. Now, if you want to automate this and you don't want to go measure the tube and have to empty it regularly or something, you can use a tipping bucket rain gauge. A tipping bucket rain gauge has a funnel, and then it has little buckets that fill. And every time they fill up, they tip and switch to the other bucket, and it gets recorded. And each bucket fills with a known amount of water that corresponds to a certain height of rainfall. So this records 0.01 inches each for each bucket that fills up, and gives you a recording of how much rain has fallen. So that's how you can get an automated electronic instrument that you don't have to pay attention to. You don't have to go empty or do anything to on a regular basis. So it just records how much water actually comes through with these tipping buckets. Each one has a known volume before they tip and empty out, and it counts how many times it tips back and forth, and that corresponds. Each little bucket is a certain amount of rainfall, so that tells you how much rainfall occurred. And it gets recorded over time electronically. Now, snow gets measured in 2 ways. Because one, you can go measure the depth of the snow. So you can put out a board, let the snow fall on it, and stick a ruler in it. You can also measure the water equivalent. You can melt the snow, measure how much water you get, and calculate, the amount of height of snow it corresponds. The general ratio is about 10 snow units to 1 water unit, but the density of snow varies a lot. It can get packed denser, it can be more loose. There's a lot of variation. That varies wildly. A good rule of thumb is 10 snow units to 1 water unit. So you could have you could melt some snow from a certain area and then measure the amount of water and use that. But yeah, so those are the ways to do it. And the depth can be problematic also, just because snow can get blown around and pile up in certain places. So it can get a little tricky for snow. You can also use radar to measure the rate of rainfall, because radio waves can penetrate the clouds but will reflect off of larger water droplets. You can basically measure the amount of falling water in the clouds and use that to figure out how much rainfall has happened. And this is convenient because it can be done basically remotely. So here is a Doppler radar display showing precipitation. This is produced by the National Weather Service. So here are places with light to heavy precipitation. There are more big rain droplets where it's redder and fewer where it's bluer. And also with Doppler radar, by using the Doppler effect, you can measure how clouds move. So you can measure things like rotation and stuff, which lets you do things like see if something is maybe going to turn into a tornado, which is always a good thing to know. And that was the end of chapter 17. So let's go on to chapter 18 and talk about air pressure and wind. We'll define air pressure. We'll describe the instruments used to measure air pressure. We'll discuss the 3 forces that act on the atmosphere to either create or alter winds. We'll contrast the weather associated with low pressure centers, cyclones, and high pressure centers, anticyclones. We'll go over Earth's idealized global circulation and describe how the continents and seasonal temperature changes complicate this pattern. We'll look at 3 types of local winds and describe how they form. And we'll look at the instruments used to measure wind and explain how wind direction is expressed using compass directions. And we'll look at the Southern Oscillation and its relationship to El Nino and La Nina, and the climate impacts of El Nino and La Nina in North America, and the major factors that influence the global distribution of precipitation. So, you are currently under pressure from the air. You are feeling the weight, the force exerted by the weight of all the air above you. And it's applying a force of about 14.7 pounds to every square inch of your body. 14.7 pounds per square inch. It's about a kilogram per square centimeter. Now, this pressure decreases with increasing altitude. So if you go up in an airplane, the air pressure up there is quite a bit lower. In fact, they pressurize airplanes because the air pressure up there is quite a bit lower, which is why, if the plane loses pressurization, the little masks drop from the ceiling and you put a margarine cup over your face. Because there's less air up there. So the amount of air decreases with the air pressure. Now, the unit that is most commonly used to measure air pressure at the Earth's surface is the millibar. And that is because standard sea level pressure is 1,113.2 millibar. That's like the standard number. And the variations, it varies from 900 something millibar up to maybe 1,100. So millibars, the scale of the variation in pressure is in the millibar range, up to 100 something. So that's just why millibars are commonly used for weather. So 1 bar is a nice round number in SI units for pressure. So the SI unit of pressure, which is a Newton per square meter, is called the Pascal. 1 bar is 100,000 pascals. It's 10 to the 5th pascals. And it's a useful unit because it's almost 1 atmosphere, but it's a nice easy number to do calculations with because it's a nice round number of newtons per square meter. And then millibars are thousandths of a bar. So a millibar is 100 pascals. And they're useful because the variation scale for weather is around the millibar range. You can also measure in pressure in pounds per square inch. It often gets measured in inches or millimeters of mercury. There's a million units for pressure. Pressure is like got way too many units. But so sea level pressure, what you are feeling is the weight of all the air above. And it adds up to about 14.7 pounds per square inch. Some other things. So one of the ways you can measure pressure is with a mercury barometer, which is a tube of mercury that is inverted into a pool of mercury. So there's a vacuum above the mercury on top, and the air pressure is holding up a column of mercury. And the height of that column tells you the pressure. So 2 of the common units are millimeters or inches of mercury. 29.92 inches of mercury is standard sea level pressure, or millimeters of mercury. It's 760 millimeters of mercury. Millimeters of mercury are also called torr because there are too many units for pressure. So the mercury barometer was invented by Torricelli in 1643. It's still the standard. It uses a glass tube that balances mercury and air pressure. The problem with a mercury barometer is that it's a 30-inch long tube filled with liquid mercury that is exposed to the air. It's just an awkward thing. And it's full of mercury. So it's also moderately toxic. Liquid mercury is not actually that bad. It's mercury compounds that are problematic, but you don't want to have liquid mercury around. But it's also just like, yeah, you need a 30-inch long tube. They're really big and awkward. They have to be like 3 feet long. An aneroid barometer, aneroid means without liquid, uses an expanding chamber. And one of those, you could just have a thing about this big, fits on your wall. Expands and shrinks. Or you could have even smaller ones. I mean, they fit them on chips now. So in the modern day, if you want to measure air pressure, you can fit an air pressure sensor down to this big. But you could make like a mechanical aneroid barometer that has a dial that you read off that's based off of, it has like a little metal, partially evacuated metal chamber that as the air pressure goes up, it shrinks, and as the air pressure goes down, it expands, and that moves the needle. An aneroid barograph is one that continually records air pressure. So this is a simple mercury barometer. It's a tube with mercury in it in a container. And you measure the height. It's 76 centimeters or 29.92 inches. That's standard atmospheric pressure. Here's what one actually looks like. It has to hang vertically. And, you know, there has to be access to air pressure to the mercury surface. So just kind of an awkward thing. Can't seal it like you can a thermometer. An aneroid barometer, on the other hand, uses a partial vacuum chamber like this that when the pressure goes down, it will expand a little. When the pressure goes up, it will shrink a little. That pushes on the set of levers, which rotate this dial, the pointer, and that points to different pressures. And then there are electronic ones. But they work on a similar principle to the aneroid one. They have a little chamber that shrinks or expands, and you measure the size of that chamber. You might be measuring the size of that chamber electronically. It might be that it acts like a capacitor. It's got a metal plate on both sides, and the capacitance changes with the distance. And here's an aneroid barograph. It's a similar thing. It's got a stack of the chambers, so it can push a little harder, and it moves up and down along here. And you can see this measures from about 950 up to about 1050. That's sort of the range of normal atmospheric pressure, which is why millibars are useful. So wind is the horizontal movement of air from areas of high pressure to areas of low pressure. So pressure is just force being applied on everything. So if you have an area with a high pressure next to an area with a low pressure, the high pressure side is pushing on what's in the middle more than the low pressure side is. So that stuff in the middle will move towards the low pressure side, and you get wind. So the things that control what happens with wind. There is the pressure gradient force. The pressure gradient force is the force caused by the fact that there is a gradient of variation in pressure. If we want to figure out what direction the pressure gradient force is looking at a map, what we do is we'll draw lines of equal air pressure. These are isobars. And then the pressure gradient force will be perpendicular to these lines. Because these lines are constant pressure, there's no change. The pressure gradient will be changing over distance. So it'll go from high to low, and it'll go perpendicular to the lines that are at constant pressure. So here we have lines of constant pressure that are equally spaced. Each one is 2 millibars, 4 millibars apart. And here where they're further apart, we have a weaker pressure. And here where they're closer together, we have a stronger pressure. Because the closer together our isobars are, that means the faster the pressure is changing, so the bigger the pressure gradient is. You can think of it like a slope. These are at a higher slope, these are at a higher altitude, these are at a lower. When the lines are closer together, it's like a steeper slope, going down slope faster. But just in general, the pressure gradient force will go from high pressure to low pressure. And when the lines are far apart, it'll be weaker. When the lines are closer together, it'll be strong. So when you have a low pressure gradient, you'll have weak winds. When you have a high pressure gradient, you'll have strong winds. So here we have a weather map. And you can see, and these are little things showing the wind. These are like weather vanes. So these arrows point in the direction the wind is coming from. So here the wind, is blowing this way. And here the wind is blowing this way. So you'll see on here, where the lines are closer together, over here, these are higher speeds, because the little symbols on the end indicate the speed. Where the lines are further apart, you have much lower speeds. And you'll see that sort of roughly, things go from high pressure to low pressure. It's not quite exactly high pressure to low pressure because there are other factors that affect it. So pressure gradient force is not the only thing that affects wind. It's the thing that provides the force. Then there's another effect called the Coriolis effect due to the fact the Earth is spinning that bends that wind in the northern hemisphere to the right. And here is a short video about isobars on weather maps.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. This time we're going to take a look at how we represent air pressure on weather maps. We use a graphical device called an isobar. We measure air pressure with a variety of different devices. This is a barograph here that records changes in air pressure over time. Over this section of the continental United States, we might have a bunch of different meteorological stations where we're measuring the air pressure. So let's say this is all data from 10 a.m. on a particular day. And this is the air pressure as represented in millibars. This information is good, but it can be more accessible if we organize it. So basically what I'm going to do here is I'm going to draw on some contours to this data. So basically I'm going to draw a line here around all the values on the map that are less than 990 millibars. And you can see there's only one value on the map that's less than that number. Now I'm going to draw a second contour, and this is basically the 1000 millibar contour, or the 1000 millibar isobar. Isobars basically are lines of equal air pressure. And so everything inside that line is less than 1000. Everything outside that line is more than 1000. Let's go ahead and draw in one for 1010, 1020, and 1030. There's only two values on the map that are greater than 1030. So those are over there on the far right in New England. So we can do two things at this point. Now that we've drawn on these isobars, we can say we've got a low pressure system here over Arizona, and we've got a high pressure system here over New England. And of course, the air is going to want to move from high pressure towards low pressure. So we'd end up seeing arrows on the map that basically represent at least initial wind directions that look something like that. Now the Coriolis effect is going to complicate that, and there are other variables, but that's the basic idea. In order to understand how this relates to wind, you need to understand that the closer the isobars are to one another, the greater the pressure difference, or the greater the pressure gradient. And so you're going to get stronger winds where you have a higher pressure gradient, and weaker winds where there's a weaker pressure gradient. So in terms of the previous picture here, we would expect to see very weak winds over here where the isobars are not closely packed together, and we'd expect to see much stronger winds where they're very closely packed together over here. Okay, this is the figure from your textbook. You can see here that we've got a map of the 48 contiguous United States and adjacent portions of Canada and Mexico. And we have isobars that are drawn on here in a 4 millibar interval. That's in contrast to the 10 millibar interval that I used on my example a few moments ago. You can see here that we obviously have a low pressure area which is centered over southern Lake Michigan, and we've got a high pressure area which is centered over Alberta. The next thing that we can show on this map is how that relates to wind direction. So we've got this key over here that basically shows us the different symbols for winds of different speeds. The little head on each of these symbols basically is showing the direction that the wind is blowing toward. So with the example of this low pressure system here, the air is going to want to move in towards that low pressure area from surrounding high pressure areas. But because of the Coriolis effect, it's going to take on a path that is diverted a little bit to the right of the path it would take on ordinarily. So that's why you can see these things are oriented a little bit right of perpendicular to the isobars. Another thing that I would note is over here you can see there are very gentle wind speeds, basically from completely calm to up around 8 miles per hour. But where the isobars are closely packed together, you can see that there are much larger wind speeds in there that are on the order of 50 or 60 miles an hour. Okay, so what would the isobars look like for this low pressure system here? This is a tropical cyclone, and you can see here that the winds are moving in an inward direction. So what does that indicate about the pressure system, and how would you show that in terms of isobars? Well, obviously you've got to have a low pressure system here in the middle, so the air is moving in towards that low pressure system, and basically then it would probably have the isobars very closely packed immediately adjacent to that low pressure zone, and then they would get increasingly spaced apart as you got further out away from it. Thanks very much for your attention. This has been another Smart Figure.
Well, there's a number of factors that lead to the fact that we have a lot of wind. That's not the actual original origin of that name. Originally was talking about the fact that our politicians were full of hot wind. So, well, we do have a lot of wind. The original origin of that name was actually an insult. But we have a lot of wind actually because we don't have a lot of stuff to stop the wind. So there's not a lot of friction to slow wind down. That's part of it. There's other factors involved. But yeah, the original origin of that was politicians talking a lot of hot wind. As mentioned in that video, one of the major factors for wind is the Coriolis effect. We are on a spinning ball. And because we are spinning, as something moves across, the Earth rotates underneath it. And that has the effect of effectively causing things to turn to the right. Well, in the northern hemisphere, it turns to the right. In the southern hemisphere, it turns to the left. So it's not, you're not actually being deflected. If you were outside of the rotating reference frame that we're in, so if you were like still above the Earth, things affected by the Coriolis effect would kind of go in a straight line and the Earth would turn underneath them. It's a little more complicated than that, but this is the thing that happens in anything that's rotating. And you can get some really funky effects out of it. Like if you put a ball on a record player, you can get some really strange effects. But the general effect is, if you are on a ball, anything that is moving through the air will be deflected with a force that is an apparent force that is proportional to how fast it's moving. and it's deflected towards the right in the northern hemisphere and towards the left in the southern hemisphere. And this is why this deflection is what causes cyclones, hurricanes, all to spiral around like that. And you may have heard that it's what causes, the water in your drain to spiral around. This is not the case. The force is not strong enough to actually, the water in your drain spirals around because of other forces, mostly based on the shape of your sink or whatever. To actually get the Coriolis effect to have an effect, unlike the water in your drain, takes very careful work. But Coriolis effect, it affects, the wind, deflects it to the right, but it's also like if you have a naval gun and are firing, shells a long distance very fast, you have to take it into account because it deflects those to the right. It deflects everything to the right in the northern hemisphere. It's to the left in the southern hemisphere because they're on the bottom. Now, near the surface, another major effect is friction. This will act to slow the air's movement down, where it will interact with the surface and it will be slowed down. So the Coriolis effect, basically, if you're aiming for some point on the equator, once you get there, the Earth is rotated out underneath you, and so that effectively deflects you to the right. So here is a short video about the Coriolis effect. This is something that happens with any spinning object.
The Coriolis effect.
Coriolis effect, sorry.
As a result of the rotation of Earth, the path of any free-moving object will be deflected to the right in the northern hemisphere and to the left in the southern hemisphere. This deflection is known as the Coriolis effect or Coriolis force. We first look at the path of an airplane traveling from the North Pole toward the equator. Notice that the path of the airplane on a non-rotating Earth is a straight line from north to south. Notice that once the airplane begins to move away from the North Pole, it continues to move toward its original target at the equator. However, because Earth is rotating, the path traced out by the airplane exhibits a deflection to the right. The rotation of Earth has caused this deflection. The deflection of the Coriolis effect occurs regardless of the direction of movement. Next, we look at the path of an airplane flying west to east from San Francisco to New York City. Notice that the path of the airplane on a non-rotating Earth is a straight line from west to east. Notice that once the airplane begins to move away from San Francisco, its path is deflected to the right by the Coriolis effect. The amount of deflection from the Coriolis effect varies by latitude. The deflection is greatest at the poles and diminishes toward the equator. At the equator, there is no Coriolis effect deflection. In addition, rapidly moving objects are deflected more than slowly moving objects. The Coriolis effect influences many patterns in physical geography. For example, major ocean currents exhibit deflection to the right in the northern hemisphere and to the left in the southern hemisphere.
So the combination of those three factors, pressure gradient force, the Coriolis effect, and friction, leads to certain patterns in the way that wind blows. High up in the upper atmosphere, upper air winds actually end up blowing parallel to isobars because they get bent by the Coriolis effect until they're going parallel at right angles to the pressure gradient force. Because the Coriolis, they go faster and faster and get bent more and more until they reach a point of stability where the Coriolis effect is pushing them one way and the pressure gradient force is pushing them the other way. And they end up with these blow parallel to isobars, so they blow along the same direction as the along the isobars, and these are called geostrophic winds. This lack of friction with the surface allows for high speeds, and you get what are called jet streams. These are like rivers of air at very high altitude. They travel at very high velocity, hundreds of kilometers per hour, like 120 to 240. And were actually discovered by the Japanese shortly before World War II. And there was an attempt to use them to send balloons across the Pacific Ocean and drop things on the bombs on the US. But it turned out to be really not easy to aim. And then they were better understood during World War II when we started flying airplanes up that high. So what happens with geostrophic wind is you have some wind that starts like this, there's pressure gradient force, so the wind starts going this way. Pushed by the pressure gradient force, it goes faster, the Coriolis effect gets bigger and bigger, until eventually the pressure gradient force and the Coriolis effect balance each other out, and the wind travels parallel to the isobars. So because there's no friction, the pressure gradient force will continue pushing it towards the low pressure end, but it will get faster and faster as that goes on, and that will make the Coriolis effect bigger and bigger. And the Coriolis effect is always trying to turn you to the right. And so the Coriolis effect will keep turning you to the right until it balances the pressure gradient force. And once they're balanced, the wind will flow parallel to the isobars. So that's geostrophic wind. High altitudes, no friction. Now, near the surface, friction fights back against the pressure gradient force. So you're much closer to going straight from high to low near the surface because there's friction. So these three forces, the pressure gradient force, friction, Coriolis effect, all balance out, and you get a stable wind at some angle to the right of your pressure gradient force. And it will vary from the surface up to the upper level wind as friction is reduced. So here we have winds aloft versus surface winds. So here we have the high level winds where pressure gradient force is balancing the Coriolis effect. There's no friction. They end up parallel to the isobars. And then as you move down, friction starts to kick in. The wind gets slower, and the pressure gradient force is balanced by a mixture of friction and the Coriolis effect. So the wind gets closer and closer to the direction of the pressure gradient force. Because the friction always points against the wind, the pressure gradient force always points in the same direction, and the Coriolis effect is always at right angles to the wind. And so down near the surface, the wind is much closer to pointing in the direction of the pressure gradient force. And because the wind is slower, the Coriolis effect is smaller. So it has less effect. Now, there are both high and low pressure areas, and the winds spiral around both high and low pressure areas. Cyclones are low pressure areas. They're low pressure at the surface. They're associated with rising air. So you have winds going in and air rising up. So they're centers of low pressure. They often bring clouds and precipitation because that rising air, as it rises up, the water vapor in it condenses, creates clouds and precipitations. So low pressure cyclones, you get rain. Which is why if you look at the barometer, back in the barometer section, you'll notice the low pressures were labeled stormy or rainy, and the high pressures areas were labeled fair and clear. High pressures are anticyclones. They're associated with sinking air. This is a center of high pressure where air from above is coming down and spreading out. The pressure increases towards the center. The air blows away from this. But because this air is coming from high in the atmosphere, it's really dry. So you don't get any rain. In the northern hemisphere, cyclones, the winds, because the winds going inwards are deflected to the right, this causes the winds to spiral around the cyclone counterclockwise. So the winds will travel around a low pressure area counterclockwise. If you have a dramatic low pressure area called a hurricane, you will see the spiraling of the clouds and all the winds for a hurricane go counterclockwise. Anticyclones are the opposite. They're high pressure areas. In the northern hemisphere, they go clockwise. These are reversed in the southern hemisphere because the Coriolis effect is towards the left in the southern hemisphere because they're upside down compared to us. So yeah, it's the same effect. It's just you're looking at it from the other side. So it's effectively flipped. So hurricanes in the northern hemisphere are counterclockwise. Typhoons, I think they're called typhoons sometimes. In the southern, actually, those are just the Pacific. If you have stuff in the southern hemisphere, they're the other direction. I think they actually get called cyclones. So a cyclone is a center of low pressure. The pressure decreases towards the center, and the winds associated with the cyclone spiral inwards. This is for the northern hemisphere. I would admit a northern hemisphere bias. I live there. So do most people on the planet. But in the northern hemisphere, the winds are associated with the cyclone, converge inward and rotate counterclockwise. In the southern hemisphere, they still converge inward, but they rotate clockwise. So if you have a cyclone in the southern hemisphere, so like in Cyclone Alley, outside of Australia, those will be rotating clockwise instead of counterclockwise. An anticyclone, the winds associated with an anticyclone move outwards. It's a divergent pattern. In the northern hemisphere, they go clockwise, as shown here. You can see everything is turning to the right, and so the winds go clockwise. In the southern hemisphere, they go counterclockwise. This is associated with subsiding air dropping from higher altitudes. This is usually brings fair weather, nicer weather. That's because that air is dry. There's not a lot of water in it. There's not a lot of stuff in it. So, and it's sort of the opposite structure on top. So at a high pressure thing, it's converging on top and diverging on the bottom. And and the low pressure area is diverging on top and converging on the bottom. So these are cyclones and anticyclones.
Cyclones. A center of low atmospheric pressure is known as a cyclone. Notice that air near the surface converges into the low in a counterclockwise direction. The cyclone shown is in the northern hemisphere. As air spirals upward in the cyclone, the wind flow becomes increasingly geostrophic. After ascending, the air diverges into the overall geostrophic upper atmosphere flow. As air rises, it undergoes adiabatic cooling, which may lead to cloud formation. For this reason, cyclones are generally associated with clouds and often precipitation. Anticyclones. A center of high atmospheric pressure is known as an anticyclone. Wind in the geostrophic flow aloft begins to descend toward the surface high in a clockwise direction. The anticyclone shown is in the northern hemisphere. As air spirals down in the anticyclone, the wind flow becomes less geostrophic. After descending, air diverges in a clockwise direction along the surface. As air descends, it undergoes adiabatic warming, which reduces the likelihood of cloud formation. For this reason, anticyclones are generally associated with clear and dry conditions.
So there are large-scale general circulation patterns for the whole atmosphere of the Earth. And the underlying cause of this is unequal surface heating. Basically, the equator is warmer than the poles because the equator gets more direct sunlight than the poles. But because the Earth is spinning, instead of just getting one big cell that goes from the equator, you have rising air at the equator and sinking air at the poles, and you have one big cell covering the Earth. We end up with three pairs of atmospheric cells. So we have three cells going from the equator to the pole. And that's because the spinning of the Earth causes those cells to basically get affected by the Coriolis effect. You get multiple cells because the air gets bent and drops down, and you get sort of a repeating pattern. Same thing happens on other planets. That's why Jupiter has all those bands. When we looked at Jupiter and it had banding, those were convection cells, like we're about to see here. So in the ideal globalized circulation, there's an equatorial low pressure zone where you have rising air and abundant precipitation. At the equator, it's the warmest, air goes up, dumps water out, it rains on you a lot. Then there's a subtropical high pressure zone where you have subsiding, stable, dry air. It's about 30 at about 30 degrees latitude. This is the location of the great deserts. The Sahara Desert is here. Several of the Asian deserts are in this. In the southern hemisphere, I think much of the center of Australia is in this, and above and below this are around this are the trade winds and the westerly winds. So because the airflow, so there's an airflow from the high pressure zone at the subtropical high pressure zone to the low pressure zones on either side. And then that air gets bent by the Coriolis effect towards the right. And so you get the southeasterly trade winds and the westerly winds. We're in the westerly winds to the north of the subtropical high pressure zone. But if you go a bit further south, you get easterly winds, the trade winds, which is why trade across the Atlantic was so easy, because you travel a bit north, you get the westerlies that blow from the west, which will carry you towards Europe. You travel a bit south, you get the trade winds, which will carry you west back towards the Americas. It's very easy to go back and forth. Then, so the westerlies are between the subtropical high pressure zone and the subpolar low pressure zone. At the subpolar low pressure zone, warm and cool winds interact. You get a polar front with areas storms. The polar vortex is around there-ish. Well, it's a bit north of it. And when it dips down, we get that polar vortex effect. And then there's the polar high pressure zone, which has cold subsiding air, polar easterly winds, and the polar front. So here are sort of what they are. You get rising air at the equator. It sinks down around 30 degrees. you can see where the Sahara Desert is, where some of the deserts in the US are, in the Southwest, things like that. And then it rises, and then there's the subpolar low with rising air over here, the polar front, which can dip down into this. You can see how air coming from the subtropical high, going north towards the subpolar low, bends to the right to form the westerlies, which is what we're in the middle of, and most of the US is in the middle of. And when it travels south towards the equatorial low, it bends to the right to form the northeast trade winds, which carry along this way. And then there's the southeast trade winds here. This is the doldrums. And then there's the polar easterlies up here, and there's the polar easterlies there. And there's another set of westerlies and polar easterlies down there. But this is sort of an ideal thing. So we have 3 cells from the equator to the pole. Jupiter, because it's bigger and spins faster, has more. So it's got more stripes. So here is a short video about the global circulation pattern, the general circulation pattern of the air over the entire globe.
Hello, this is Callan Bentley. Welcome back for another Smart Figure. This time, let's take a look at the global circulation of air in the atmosphere. If you look at an average global circulation map for the month of January, it looks something like this. You'll note that there is this zone along the equator called the Intertropical Convergence Zone, the ITCZ, shown by the purple line here. And that sort of connects up a series of low pressure areas. And then both north and south of that, there's a series of high pressure areas. So here's like a line of high pressure areas south and another line to the north. And then more towards the pole from there, you've got some low pressure areas as well. Doesn't show up as well down in the southern hemisphere. So what's going on with this overall pattern? Why do we see this? Well, we can start off by considering first off a non-rotating Earth, where basically because of the influence of the sun's rays, so let's consider the sun's rays coming in here from the side and warming the planet, you'll notice that they hit more directly at the equator and they hit more obliquely or glancingly towards the poles. As a result, the Earth is heated unequally and it gets hotter at the equator than at the poles. So what you would expect there is that the warm air would rise away from the surface at the equator and that it would sink towards the surface at those cold polar regions. So you'd end up getting these convection cells that develop on the surface of the Earth, and there'd basically be one cell in the northern hemisphere and there'd be a second cell in the southern hemisphere. That's not what we really see though. Because the Earth rotates, we actually end up getting a series of approximately 3 cells in each hemisphere. Let's consider the situation at the equator first. Again, we have warm material rising off the surface at the equator. As more warm air rises beneath it, it gets shoved both north and south of the equator, and then it sinks back towards Earth's surface at around 20 degrees or 30 degrees away from the equator. These cells end up producing trade winds at the surface. So if you think about those arrows, those red arrows there blowing over the surface, they end up basically being deflected a little bit to the right of their path in the northern hemisphere and a little bit left of their path in the southern hemisphere. So they end up taking on these sort of curved approaches like the arrows you see in the middle of the screen. You'll notice that those arrows converge towards the equator. That's that intertropical convergence zone that we mentioned. And overall, these sort of 3-dimensional bubbles that you see here are called Hadley cells. These Hadley cells are important cells of circulation that occur in Earth's atmosphere. Now, north and south of the Hadley cells, there's a similar looking arrangement. And there, between the subtropical high and the polar front, you've got another ring-like circulation cell that produces the westerly winds. And again, just look at those arrows that are flowing over the Earth's surface and think of them being deflected a little bit to the right in the northern hemisphere and a little bit to the left in the southern hemisphere, and you'll understand where the westerlies come from. Finally, at the pole itself, you'll find that there is another convection cell, and that convection cell is the polar high. You'll notice that it produces polar easterlies. Okay, so we end up basically with this sort of series of rings of circulating atmosphere over the surface of the Earth, almost like the planet is wearing a series of inner tubes that wrap around it, and these inner tubes are internally rotating over time. So how would that affect precipitation patterns? Well, here's an answer. If you look at the continent of Africa, you'll notice that Africa has a band of moisture that stretches across its midsection, right around 0 degrees of latitude, the equator. And then there are bands of desert that are about 20 degrees north and 20 degrees south of the equator. Basically, what's happening here is that the air is being warmed at the equator. It's rising away from the surface of the Earth, so I've chosen to represent that here with these little red symbols. So think of that as air mass moving up towards your perspective as you're looking down on this scene. And then the next step, of course, is for the air to flow away and flow both north and south of the equator. So that's what's happening here. Then it sinks towards the Earth's surface, as shown by these little blue symbols. And that sinking air is going to be really of different character than the rising air. So the rising air would be all saturated with water. It would cause lots of rain, and that's a lot of precipitation right there at the equator. But the sinking air basically has had all the moisture wrung out of it, and so when it sinks, it's quite dry. And so you end up getting these high pressure zones there where you have relatively dry air and big bands of desert. This circulation cell, this Hadley cell, would not be complete until we had the air moving back toward its origin, moving back towards the equator. And again, in the southern hemisphere, that's going to, due to the Coriolis effect, the actual wind path is going to look something like that. In the northern hemisphere, it's going to look something like that instead. Hopefully you got that right. Thanks a lot for your attention. This has been another Smart Figure.
Now, this is not only influenced by this cell pattern, the continents have an effect, because the continents change the way the water, the air accepts water, but also they change temperature and such. So seasonal temperature differences disrupt the global pressure patterns and the global wind patterns. And the continents change temperature more than the ocean. So these effects are more obvious in the northern hemisphere than in the southern hemisphere, because the northern hemisphere has more land. So some effects of this influence. You can get monsoons that occur over continents. During the warm months, air flows onto the land. You get warm, moist air from the ocean. You get lots of rain. During the winter months, air flows off the land. You have dry continental air and minimal rain. Because during the warm months, the land is hotter than the ocean. So air is going to flow. So that's going to be lower pressure. Where it's hotter, air is going to flow from the ocean to the land. During the winter months, the air will flow off the land to get dry continental air. So for example, here in January, you can see here we have the Siberian high and India, which gets monsoons. There are other places that get monsoons, but India is a good example. You can see the air is flowing down and off the land into the ocean, and you get monsoon. So you have very dry air in the winter, the cool months. But in July, when it's warmer, and you can see the ITCZ has moved on, then the air is flowing in from the ocean and it dumps huge amounts of rain. So in regions that have monsoons, you tend to have a dry season and a rainy season, not so much summer, winter, fall, spring. You have wet and dry. We live in the westerlies, in the mid-latitudes. In the westerlies, the airflow gets interrupted by cyclones. The cells will move west to east in the northern hemisphere. This creates cyclonic and anticyclonic flows. And the paths of cyclones and anticyclones are associated with the upper level airflow. So often they'll be moving from east to west. So you see that with hurricanes. I think that is where I'm gonna stop for today. So, any questions about anything? Okay, have a nice day. I'll see you all on Thursday.